Okay, this is the review for logarithmic and exponential functions. So first thing is you need to be able to plot exponential functions, and as long as you know the parent function for each one and also knowing the normal transformations, you'll be in good shape. So let's start with the exponential function, some number to the x power. So let's say 2 to the x power. So y equals 2 to the x. So this exponent can be, the base of the exponent could be any value. It could be e, it could be 3, it could be 4. And you can usually get at least a couple of points to plot fairly easily. So if you let x be this column and then y be this column, you would pick probably, you could pick -1, 0, 1, and 2. So if you use -1, you'll get x 2 to the -1 power, which is 1 over 2. So you get 1/2. And any number raised to the 0 power is 1. And 2 to the first power is just 2. So, the first power is always just going to be the base. And to the -1 is 1 over the base. And then you've got 2 squared, which is 4. 2 to the second power. So if I plot those points, I'd get at -1 I'd get 1/2. At 0 I'd get 1. At 1 I'd get 2. And at 2 I would get 4. And in this case you could do x equals 3, and that would be 8. And you always have this approaches the x-axis. So once you get this fractional part, the rest of it you just slowly approach. And then it goes through there. So, if I had y equals 3 to the x, then I could do a table like this as well. And I'd have -1, 0, 1, and 2. And here you'd have 1/3, 1, 3, 9. So that one would look, this would be below this curve, 1/3, still go through 1, x equals 1, y equals 3, x equals 2, y equals 9. So the higher the base, the more quickly this thing climbs like that. So you should be able to, I'm not going to give you 5 because that would just go, it's going to be either 2 or 3 or e to draw the base. And then you have the normal transformations. So let's say we start with this. So if I add 1, that's y shift a +1. If I did y equals 2 to the x minus 1, so the argument of which is the exponent, this would give you an x shift of +1. Remember, when you have the x shift, you take the opposite of the number here. It's x minus h. So if this is x minus 1, you shift it +1. If it's x minus 2, you shift +2. If it's x +1, you shift. So those are the x shifts. And again, what you're doing is taking this parent function, you're moving it up or down or left or right. Then you have a negative sign out front. And what that does is things that were positive now come negative. So this is a x-axis, what do we call that thing? Reflection. So an x-axis reflection would, you just do all the points below the x-axis. So it would look something like that. So it'd have the same shape, you just go that direction. And then the third, or the last transformation, is if you had 2 to the minus x. So the exponent is changed. That's a y-axis reflection. So what would happen is this would stay the same because it's on the y-axis, but this would move over there, this would move over here, this would move up to there, and then it would come down, you know, kind of like this, and then it would approach the x-axis from above. And of course, then you can have combinations. You know, I could have y equals 2 to the x plus 3 minus 2. So there I would have a y shift of -2. I'd have an x shift of positive or -3. One thing to watch out for is if you have 2 to the -x plus 1. Anytime you have a negative in front of the x in the argument, you factor out the negative sign. So what that does is it makes this positive inside the parentheses, and you change the sign of the second part, so that becomes -1. So here you have, if you go back to this list, you have a y-axis reflection. So this, if I asked you what were the transformations, I'd say y-axis reflection and an x shift of +1, because I have a negative sign inside the parenthesis term. So make sure you factor that out. So that's the exponential function. Now if you look at the logarithmic function, it looks pretty close to the same thing, because they're inverse functions. So let's say I had the log base 2 of x. That's the parent function. So again, I could plot 4 points. I could plot x equals probably -1/2, or not -1/2, 1/2, 0, 1, and 2. It's kind of the opposite of what I did over here. Here I did here I did -1, 0, 1, 2. 1/2, 1, 2, 4 actually is what I would choose. So that's not correct, because I can't let x equal 0. So it's kind of the opposite. So I'd have 1/2, 1, 2, and 4. And the corresponding y values would be -1, 0, 1, and 2. So if I plot x equals 1/2, y equals -1, that's that point. X equals 1, y equals 0, that's that point. X equals 2, y equals 1, that's that point. And x equals 4, y equals 2. And also I could do x equals 3, y equals 8. And then in this case, the function approaches the y-axis instead of the x-axis. So that's my parent function. You know, and again, if I had log base 3, I'd still go through 0, but I'd have a third here. I'd have 3. At 3, I'd have 1. So x equals 3, y equals 1, and then x equals 9, y equals 2. So it's, you know, it's a sharper. It goes flatter more quickly, and then it kind of loops down like that. So that's how you get some points to guide you on these parent functions. Now, as far as the transformations are concerned, again, if you had log base 2 of x minus 4, this would be a y shift of -4. That'll be shifted down. If you had y equals log base 2 of x plus 1, then that would be an x shift of -1. You take the negative of that. If you have y equals log base 2 of negative x, that's the y-axis. reflection. And if you had y equals negative log base 2 of x, then that's an x-axis reflection. So a y-axis reflection is going to be on this side of the y-axis. So you'd plot the same points. So you'd have 1, 2, so it'd be negative 1 comma 0. So we're doing this one right here. Negative 2 comma 1, negative 4 comma 2, negative 8 comma 3. So it has the same shape except it goes the other direction like that. So that's a y-axis. Approaches the x-axis down here. I mean the y-axis. Now this one, what happens is the positives becomes negatives and negatives become positives. So we go here again through 1 comma 0. This point would come down there. This point would come down there, and this point would come down there, and this point would be there. So instead of approaching the y-axis from the bottom, you'd approach it from the top. So that's this one. The blue is that one, and the black is the original one. And then you can combine them, into one. So if I had y equals log base 2 of negative x plus 3 plus 2. Again, when you have a negative inside the argument, you're going to factor that out, not of the argument, but just out of the two terms. So instead of negative x plus 3, it's going to be negative the quantity x minus 3. So here we have a y shift of plus 2. We have x shift based on this, and the x shift is positive 3 because we take the negative of that. And because the negative sign's in here, we're going to have a y-axis reflection. Because you can see down here in my example, when the negative sign's in, you have a y-axis reflection. Okay, so that is that. Then you have some kind of basic things you can do with logarithms where you don't have to use a calculator. So let's say, for example, I have log base 3 of 81 equals something. Actually, 81 to the x power equals 10. So what you do here is, we need to be able to not use a calculator. We have to rewrite 81 as 3 to some power. So that's when you can not use a calculator, is to rewrite that. So 81 is 3 to the, well, let's see, first power is 3, second power is 9, 27, 81. So it's to the fourth power. So you can replace 81 with 3 to the fourth. And then you can multiply the exponents together because you're raising something to a power to another power. So that just becomes 3 to the 4x power. And at that point, you can take the 4x out, which we could have taken x out here, but then we wouldn't have been able to simplify that. So you take the 4x out, and you get log base 3 of 3 is 10. Well, log base 3 of 3 is 1. Anytime this is the same, then it's 1. So you get 4x equals 10, or x equals 2.5. So that's one way that you can use exponents. Then you have where you write an exponential equation in logarithmic form. So this would be the exponential equation. 4 squared equals 16. So when you write the logarithmic expression, first is you use this base, because this is the base of the exponent, so it's the base of the log. This becomes the argument of the log, and the exponent becomes the answer. So it's kind of like this comes there, this goes there, and that is your base. And it's because you can say, what number do I need to raise 4 to get 16? Well, the answer is 2. If I raise 4 to the second power, I get the 16. So it's doing the same thing, it's just answering a different question. Yeah, a slightly different way. And you can go the other direction too. You could say, log base 3 of, let's say, 243 equals 5. So you're given that. What's the corresponding exponential equation? Well, this is the base, so 3 is the base. This is the exponent, and this is the answer. So 3 to the 5th power, which would be 3 times 3, which is 9, times 3 is 27, times 3 is 81, times 3 is 243. That would be the corresponding one. And you can draw arrows here. This is the base. This is the argument becomes the answer, and the answer becomes the argument. Now, the calculator only does logarithms to the base e or the base 10. So if I asked you to evaluate log base, well, it depends on what calculator you have. So we're assuming that you don't have one, and don't use the built-in function to do this. So if I said, what is the log base 5 of 23? How would you do that? Well, you can either use log base 10, so you'd say log base 10 of 23 divided by log base 10 of 5, or you could do the same thing using the natural logs. These are the two options that are available. So you take the log of the argument and divide by the log of the base. And if you do both of those on your calculator, so just do them and see what you get, you should get the same number. So I'm going to do it. So log base 10 of 23 divided by log base 10 of 5, and I get 1.948. And the logarithm of 23, the natural log of 23 divided by the natural log of 5 is 1.948. So make sure you can use those to change the base if I asked you to look it up. Now for the exponents, you don't have to worry about that because you can raise any number to any power. But from the logarithms perspective, we just have two bases that we have on our calculator. Okay, now the properties of logarithms, there's three properties. One says that the logarithm of a product is the sum of the logarithms individually. The logarithm of a quotient is the logarithm of the numerator minus the logarithm of the denominator. And the final one, the logarithm of a to the b power is b times the natural log of a. And this applies for any base. I've done here natural logs, but if it was at the base 3, you could do it as the base, you can do that. So because of that, you can expand logarithms. So here I've got log base 7 of this product and quotient. So I would use both of these, actually use all of them. The first one you do is you always break them up into individual terms. So if you have a more complex fraction, the ones that are in the numerator you add together, and the one that's in the denominator you subtract. So this would become log base 7 of x cubed, which is in the numerator, plus log base 7 of the square root of y, which is in the numerator, minus log base 7 of z squared. And then you can take the exponents out using this rule. Now here I have y, square root of y, but that's the same as y to the 1/2. Replace the square root with the fractional exponent, you get 1/2 log base 7 of y minus, here we have 2 is the exponent, log base 7 of z. So that's how you would expand it, and you can also contract them. So if I said 4 log base 5 of x minus 1/3 log base 5 of y minus 2 log base 5 of z, and I want to combine those just like I separated them here. The first thing you would do is you take the terms inside. So you can go either way with this. You can go this way or you can go that way. So this multiplier becomes the exponent. This multiplier becomes the exponent. This multiplier becomes the exponent. Notice they're all the same base. That's a requirement. You can't have log base 3 and log base 2 or anything like that. They have to all be the same base. And now you can go backwards this direction. And again, if you have anything negative, that goes in the denominator of the fraction, anything positive. So we say log base 5 of x to the 4th divided by x to the 1/3 times z squared. So these two are negative, so they get in the denominator. And lastly, you can rewrite the fractional exponent as a root. So that's the cube root of y instead of y to the 1/3 power. So that's your answer. Okay, so make sure you can do that. I'm just looking through the answers. Problems. If I asked you what's the natural log of -5, you might try that in your calculator. And what you'd get is error. So anytime you have the natural log, any log of any negative number, it does not exist. You can't have negative arguments in logarithms, just like you can't have negative square arguments in square roots. Okay, now the rest of the problems are basically solving logarithmic or exponential problems. So we went through quite a bit of those in class. So I'm just going to give you a more complicated one, and then you hopefully can do the easier ones, but I'm just giving you an idea of what you might expect. So let's say we have 2 times 3 to the 3x minus 1 plus 5 is equal to 12. So the first thing you need to do is you need to get 3 to the 3x minus 1. You need to get the exponential term by itself. So that typically requires for you to do a little algebra. So the first thing I do is I subtract 5 from both sides, and I would get 2 times 3 to the 3x minus 1 is equal to 7. So 12 minus 5 is 7. The second thing I do is I would divide by 2, because that's not power, that's just a multiplier. So I get 3 to the 3x minus 1 is equal to 7/2, which is 3.5. Okay, now at that point, now I have to do something other than algebra. So you can use the natural log for any of these. For any exponential, you could use log base 3, but you can use any logarithm. And because the natural log is in your calculator, you could use either that or the log base 10, but just stick with the natural log. So in this case, to go from an exponential problem to an algebra problem, you have to do the opposite of an exponential, which is a logarithmic. So you get natural log of 3 times 3x minus 1 equals the natural log of 3.5. And because I've gotten to the point where all I have is the exponential term, I can say I can take out this exponent using this law back here that we looked at earlier. This one right here. So I can take that, I can take out the exponent. So that's where I get that to be an algebraic equation. And then I'm just left with the natural log of the original base. So then I just have to solve for x. So the first thing I would do is I would divide both sides by the natural log of 3. I'm going to go ahead and do the calculation here. You could wait till later if you wanted to, but okay, so the natural log of 3.5 divided by the natural log of 3 is 1.14. Then I would add 1 to both sides, so 1.14 would become 2.14 divided both sides by 3. And I get x is equal to 0.713. So there's my answer. So again, you ultimately want to get to this. To get to that point, you first got to add the additive inverse of the constant to both sides. Then divide by this number. Or you can multiply by the multiplicative inverse, which would be a half. So you can either divide by 2 or multiply by a half. Once you do the math there, you're now to the case where you have to use a logarithm, one of the logarithms. We use either log base 10 or log base e, which is the natural log, to get this exponent down in front. So that's the basic idea. You know, there's quite a few examples doing that, solving logarithmic equations, exponential equations. And then the other class of problems is logarithm problems. So let's do something kind of similar to what we just had there. So let's say you have 2 times the log base 3 of 2x minus 1 plus 3 is equal to 22. So again, what we want to get to is log base 3 of 2x minus 1. That's the goal, initial goal. Or we may already be at this point. So there's probably some that are this simple, but some you have a little more complexity. So again, the first thing we would do is we would subtract 3 from both sides. So that would give you 19 on the right hand side. 22 minus 3 is 19. Then you would divide both sides by 2 to get to this thing. And so 19 divided by 2 is 9.5. Okay. So I think this is about as complicated. You might have, an exponent inside here, but then you could just bring that exponent out, and then you're back. This original problem could have been presented as such. It could have been log base 3 of 2x minus 1 quantity squared plus 3 equals 22. So here I could bring the exponent out, and then you would just start from that point. Okay, so once you get a coefficient of 1 in front of the logarithmic term, you need to use exponents. In this case, it is important which base you use. You can't just pick any base. You pick the base of the exponent to be the same as the base of the logarithm. So in this case, I'd use 3. So what I'm going to do is take 3, I'm going to raise it to the log base 3 of 2x minus 1, and I'm going to do the same thing over here, 3 to the 9.5. So if you take any base and raise it to the same power, you're going to be equal. You're going to have an equal result. But I choose log base 3 because 3 to the log base 3 of that is just that thing. So I get just 2x minus 1, and then you have 3 to the 9.5 power, which is always I always pick a number that's too big. So 3 to the 9.5 power is 34,091, 92. So then I would add 1 to both sides to get rid of that on this side. So I get 34,093, 34,093. Divide both sides by 2, and I get 17,046. Okay, so that's the basic idea behind log problems. You know, if it was log base 4, I'd use 4 as the base. If it was a natural log, I'd use e as the base. So let me just pause it for a second and let you know if there's anything else I need to put on there. Okay, so that looks like it's it.